Hey everyone, and welcome to The Explainer. Today, we're taking a really structured journey from your basic, everyday intuition about chance straight into the rigorous, formal rules of mathematical probability. If you're someone who loves clear, logical building blocks, well, you are absolutely in the right place. We're going to strip away all the confusion and build up probability from the ground up. There's a fantastic quote by John Arbuthnot that really hits the nail on the head for what our mission is today. We aren't just doing math for the sake of memorizing dry formulas, right? We're using it as a candle to illuminate the dark, unpredictable unknown of chance. Mathematical reasoning is literally our tool for absolute clarity. So here is our agenda for today. 1. Defining mathematical events. 2. The algebra of events. 3. Mutually exclusive outcomes. 4. The axiomatic approach. And 5. Calculating event probabilities. Let's jump right into Section 1, Defining Mathematical Events, the fundamental basics. Okay, before we even think about calculating the odds of something happening, we have to formally establish the environment of our experiment. An event is simply any subset, which we'll call E, of a broader sample space, S. Let's ground this with a concrete example. Imagine tossing 2 coins. Your sample space, that's your S, is every single possible outcome. So heads, 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 tails, tails, heads, and tails, tails. An event is just a specific subset of those outcomes. For instance, the event of getting exactly 1 head is literally just the subset containing heads, tails, and tails, heads. We're simply grouping specific outcomes together. Now, we can actually push this definition right to its absolute mathematical extremes. Impossible events and sure events. Think about rolling a standard 6-sided die. An impossible event is rolling a multiple of 7. It simply can't happen. So mathematically, we represent that with the empty set, denoted by the Greek letter phi. On the flip side, a sure event is rolling a number less than 7. That condition covers every single possible outcome on the die, right? So it's perfectly represented by the entire sample space, S. We can also categorize these events based on, well, just how many elements are hanging out inside that subset. A simple event contains precisely 1 sample point. Going back to our 2-coin toss, getting exactly 2 tails is a simple event because there's only one way that happens, tails, tails. But a compound event contains more than 1 point. If our event is getting at least 1 head, suddenly that includes heads, tails, tails, heads, and heads, heads. It's just a much broader condition. Moving on to Section 2, the algebra of events. Combining subsets. You know, math is really just a language, and we need to translate our everyday conversational English into a format we can actually compute. When you say out loud that you want event A or B to happen, mathematically that maps to the union of sets A and B. If you absolutely need event A and B to happen simultaneously, that's the intersection. Saying event A but not B is the set difference, and simply saying not event A gives us the complement. It's brilliant. We're just turning spoken logic into strict, rigorous set theory. Which brings us to Section 3, Mutually Exclusive Outcomes, Non-Overlapping Events. Okay, so here we're introducing an absolutely crucial relationship between certain events, and this is going to dictate the grand rules we're about to establish. Events A and B are mutually exclusive if their intersection is the empty set. But what does that actually mean in the real world? It simply means they cannot possibly occur simultaneously. Think about it. You cannot roll a single standard die and get a number that is both odd and even at the exact same time. There is no overlap. The intersection is entirely empty. They are mutually exclusive. All right. Section 4, the Axiomatic Approach, the master rules. So, we've defined our events and we've built our algebra. Now we are finally ready to lay down the absolute ground rules of probability. These are the 3 master rules, the axioms. Literally every single other calculation stems from right here. Axiom 1, the probability of any event must be greater than or equal to 0. No negative probabilities allowed. Axiom 2, the probability of the entire sample space is exactly 1, meaning something from the sample space is 100% guaranteed to happen. And Axiom 3, if 2 events are mutually exclusive, the probability of either occurring is just their individual probabilities added together neatly. Let's actually see how these axioms work in practice. Because of Axiom 3, we can rapidly prove a pretty cool consequence. The probability of the empty set, that impossible event we discussed earlier, is absolutely 0. Because the empty set has absolutely no overlap with anything else. It perfectly balances our equations out to equal 0. Our foundation here is mathematically rock solid. And finally, Section 5, Calculating Event Probabilities. Calculating Outcomes. So we take this rock-solid axiomatic foundation and we use it to unlock the master formulas for complex real-world probabilities. We already know how to add mutually exclusive events, right? But what if the events can overlap? What if event A and event B share some outcomes? Well, that is exactly where the general addition rule comes in. The probability of A or B happening equals the probability of A plus the probability of B minus the probability of their interception. Now, why on earth do we subtract? Well, because if we just add A and B together, we're actually counting that overlapping intersection twice. We have to subtract it once to make sure our math stays absolutely perfect. Which leaves us with a pretty massive question to chew on. We've spent this explainer building a toolkit to predict basic things like dice rolls and coin tosses using pure, unshakable logic. But think about this. If these super simple foundational axioms hold perfectly true for a basic coin toss, how might we scale up this exact same mathematical logic to model massive, complex phenomena in genetics, or predicting markets in economics, or even training artificial intelligence? The crazy thing is, the underlying math doesn't change. Only the sample space gets bigger. Keep that in mind as you continue your learning journey. Thanks so much for exploring this structured approach with me.